A todos. O Wendelin acho que não acredita, mas a palestra vai começar exatamente às 5 horas. Você entendeu, não? Não? You may not believe it, but we're going to start on time. That's not very Brazilian and not very like IMPA, but for the Magna lectures we do that. Então, é um grande prazer apresentar o Wendelin Werner. Ele tem visitado o IMPA e o Brasil, mais geralmente, com frequência. É um amigo da matemática brasileira e de nós todos. E ele dá sequência à série de conferências magnas que o IMPA criou não muito tempo atrás e que tem sido muito bem sucedido, e certamente o Wendelin Werner vai dar sequência a essa série muito bacana. Ele é um probabilista que recebeu, dentre outras honras, o prêmio da medalha Fields em 2006. Ele vai falar sobre surface fluctuations and their geometries.
Thank
Please.
you. So thank you very much, and yeah, I have to, as you know, I'm moving soon to a country where lectures start on time, so I have to get used to that now. So I'll try to fit to that. So thank you very much. It was a pleasure to be at IMPA and in Brazil. I was sort of, as I said, it's one of the places where, as a mathematician, one feels special, appreciated, and people are helpful, and we are, it's easy to be a friend of Brazilian mathematics because Brazilian mathematics is kind to mathematicians. So I just showed you this picture that you can look at. Depending on your math background, you might detect certain features of this type of picture, and this picture will show up a bit later in the present lecture, which is about surface fluctuations and their geometries. It's actually a challenge when one comes regularly to IMPA to each time deliver a different lecture. So I was thinking, did I give this lecture before or not? I was wondering, and I checked carefully, and I thought, no, this one I haven't given here. So I hope I didn't get it wrong, but anyway. So the topic will be basically the general feature questions I want to address will be to choose at random a certain object, mathematical object, that we'd like to know, and to study it and to try to understand it. And this general idea to choose your favorite mathematical object at random and to understand it had been very useful in many instances, and you may have heard talks about random groups, random matrices, random functions, and all these things are not just for fun to say, oh, let's take a group at random and have a look at how it looks, because somehow choosing one generic group or one generic matrix or tells you something about these objects in general, and you learn something about them. And if you think a little bit about it, we'll come back to that in a moment. Choosing an object at random, just the very formulation of the question to say, what do I mean by choosing it at random? You need to put some sort of measure, you need to put some sort of mathematical structure on the set, and it's sort of starting understanding the set of structures and things like that. So in this talk, I will not do this sort of meta-mathematical discussion I just started here, but I will just say something very specific. So we'll start with sort of the first question, which is, what does it mean to take at random a function? And to try to give you some basic things that are well known about what it means to take what are the natural notions of the natural notion of a random natural function, one-dimensional function, some features of that, and then I'll try to see what the analogy, what would be the random surface version of that. So here, when I mean random surface, it's not surface in an abstract sense. It's really surface, 2 + 1 random surface. So you should really think of a random mountain. Okay. So can we do something like that? And then a bit later, can we define something related? Probably I will not have time to address that, but with sort of motivation behind. Is there a natural way to define a random distance in the plane? So you're looking at the plane or the disk, and you want to say, is there a natural way to choose at random a function, a distance between points, a random distance? And so I'll start with very basic things. And when you want to choose a one-dimensional random function, well, we don't know, the set of functions is infinite, it's continuous, it's very... so the usual trick is to discretize the problem, to say, let's look at random discrete functions, and then see whether when you approximate the continuum by discrete small steps, you can get some continuous limits and do something like that. So the natural model to, you look for when you look for the random discrete function is a random walk. So random walk is, coin tossing. You toss a coin at each step, and you look at the graph of the function you draw. And this is a somewhat provocative statement, but this is a very long random walk. Picture of a very long random walk, it's flat. Okay, that's because after 2 billion steps, in average, you have as many, coin tosses that are tails than heads. And therefore, the average, you know that unless you rescale in the vertical direction in a very clever way, what you see on macroscopic scale is flat. A very long random walk is flat. So in some sense, the provocative statement would be the natural random function is the constant function. Well, that's not very useful. So what you want to do is to stretch your very long random walk in the vertical direction. Magnify this thing until you see something. And if you magnify in the vertical direction this picture until you see something, you see basically this. Okay? The same picture, just that you see instead of taking, you see that in the horizontal direction you are between sort of minus 600 and 1,000, and in the horizontal direction you are 1 billion. So you had to stretch very much in the vertical direction in order to see this. But you see something, and this something is very interesting. It's called Brownian motion. And you should really think of Brownian motion as the random infinitesimal fluctuations away from the deterministic flat pattern. Okay? So it's there. If you look at it very closely and you stretch in the vertical direction very much, you view it in this way. So this is Brownian motion. It's a very nice object, and of course, as you probably know, it's related to all sorts of mathematics, PDEs, Laplacian, so on and so on. And it has been used in many applications as well, and it's a sort of basic tool of modern probability theory. So I just want to list a few properties of Brownian motion that, not for, because I'm going to look at what the analogy happens, what sort of analogy you can have if you look at the random mountains picture. So the first thing, it's a Gaussian random variable. So Gaussian random variable is something, for those of you who are not probabilists, you say, oh, Gaussian random variable, this has this shape, and well, why this? Okay. Gaussian random variable just means, there are three things that you should think about Gaussian random variables. The first is there's Gauss. So it's a nice mathematical object, right? Right? It's not the bell-shaped thing. No, it's a beautiful object. It's Gaussian. It's Gauss, right? It's the same Gauss than the other. So the second thing is that when you have a Gaussian random variable, that's what you learn or teach in probability theory courses, it's easy to define. you only have to, in order to describe it, you only have to describe what is called a covariance function, and this is just, a function, a very simple function. So the Brownian motion definition is just the covariance function between the Brownian motion at time s and Brownian motion at time t is the smallest value between s and t. Dot. That's the definition of Brownian motion. It's the Gaussian process satisfying. So it's easy to define. Define it for free. Now, here is something that sometimes one forgets to emphasize, about Brownian motion, and not everybody is aware of that the fact that it's actually a random continuous function was not clear from the beginning. Because if you think about this fact that you were stretching this in the horizontal direction, very, very much until you see something, you are blowing up, there's something non-trivial about it. And in particular, it's a random continuous function, but it's doing all the things you thought were forbidden for a continuous function to happen. So clearly it has infinite, it's a fractal type function, it has infinite length, it has all sorts of very wild properties. But it's continuous, and well, when you are a student and learning probability theory, you have to, you discover that this is a non-trivial proof to see that this guy is actually a continuous function. Easy to define, hard to show it's continuous. Now, it's the limit of it's independent of the microscopic model you start with. So you should think of, I take different random walks in the large scale. Basically, it's always Brownian motion, unless you are in a looking at very nasty random walks. And there is, just want to mention that there is one very natural discrete random walk that you can view as that is associated to the Brownian motion. Namely, if you take a if you take a Brownian motion here, okay, and you can just discretize it by saying, I look at where the Brownian motion is at integer times. And you can view this as this is now, a random walk where the jumps now are not integer jumps, but they are just, Gaussian random variables. But it's sort of a natural projection, natural version of the Brownian motion in the discrete setting. It has a more natural projection on discrete world than just this nearest neighbors random walk. Now, the thing that makes the Brownian motion, so natural and so interesting is its Markov property. And I just want to remind you that the Markov property of the Brownian motion means, I think everybody's seeing here, if I draw this here, I start a Brownian motion, I stop at the time t, I wait, I make a pause, and then you say, well, how does the Brownian motion continue now? You know that you have seen this. How does the future of the Brownian motion look like? Well, it's just like if you start a new Brownian motion, except that you started from here. Okay? So the way it's continuing, just like if you boot the system again, but you attach it to where you are at the moment where it's called the Markov property. Now, clearly, if it's the limit of this discrete, random walk rescaled, because the first part of the random walk is actually already a random walk, and you see that there is some scale invariance property. If you zoom into a Brownian motion, you see again something that looks like a Brownian motion. Therefore, it's a random fractal curve. Now, I want to just mention one object, because in the context that we're going to play with, it's very important to see the following variation, which is called the Brownian bridge. So if you're in the discrete world, you see we saw the Brownian motion with this very natural time parametrization. But you can see the Brownian motion as an interface. You might say, there is A here there's B, and here you have the interface between A and B, which is this random curve. In that case, there's no favor left, right, left. No favored direction. So a natural thing to do would be to consider among all, in the discrete case, among all random walks of length n, you just choose one at random uniformly among those that start at the origin and end at the origin at time n. That's a random walk bridge. It's a random walk conditioned, nailed here and here at both ends. And in the limit, when you let n go to infinity and you rescale in the same way, what you get is what we like to call a Brownian bridge, which is basically a Brownian motion, right, starting at the origin and conditioned, forced to be back at the origin at time 1. And this Brownian bridge has a symmetry property, basically you look at it this way or you look at it the other way, it has the same distribution. It's clear. Now, there's one property of the Brownian bridge. I mean, it's basically everything I said here is more or less the same, still works. I just want to emphasize one thing. So you could say, well, instead of saying that the Brownian bridge has to end up exactly at level 0 at time 1, you can say, I want it to end up at level 1 at time 1. And there's something which is true in the continuum, which is not true in the discrete setting, which is that if you look at the Brownian bridge, the flat one, conditioned to be back at the origin at time 1, and you want to compare one way, you sample this green thing, and then how do you sample a Brownian motion conditioned to be at height, say 1 after time 1? Well, you just have to add a linear function, blue function, that goes from the starting point to the end point to the previously flat Brownian bridge, and you get exactly a Brownian bridge conditioned to end up a bit up there. It's sort of a very natural, it's a very elementary thing to see and very simple to notice. So in particular, one way to simulate a Brownian bridge would just to simulate a Brownian motion until time 1. That would be the blue curve. And then you draw the blue linear curve that interpolates between the starting point and the end point. You subtract it, so the green guy would now be the difference between the blue curve and the blue linear part segment there. Okay. And the Brownian bridge, so now when you have a flat Brownian bridge like this, the green curve, you can see it as the fluctuations, infinitesimal fluctuations away, natural fluctuations away from the deterministic flat pattern of something that you can interpret as a rope or a violin string that is stretched, and fixed at both ends. Right? And therefore, the starting point and the end point both are nailed down at a given height, and in the middle, sort of this fluctuation. And you know also maybe that because of the fact that it's Gaussian random variables and that it has to do with Laplacian and so on, that you can view it as superpositions of some random harmonics and independent harmonics. I mean, there's all sorts of natural things you can play with. So in particular, the Brownian motion, you can view it also as a random Fourier series where the terms in the Fourier series, in that case, are Gaussian independent. And the Fourier series is converging in some sense because it's creating a continuous function, but it's converging, not very, very nicely because it's creating a very nasty continuous function. So there's one consequence of this little argument I just described, which is that there's some sort of Markov property of the bridge itself, even though there's no natural direction here. And the Markov property of the bridge can be understood as follows. Imagine you're looking at a Brownian motion that starts at 0 and ends at 0 at time 1. It's nailed down at both ends. And you discover the beginning of the curve. The curve up to here. How is the remaining part going to be distributed? Well, it's going to be a uniformly chosen random curve that has to go from here to there in the given time. So it's going to be a bridge from here to there in that time interval. So how do you sample it? Well, you first draw this linear thing here, and then you add a flat Brownian bridge to it, and this is the way this guy is going to continue. So there is some sort of Markov property of the bridge, and in particular, you can also do the following. Instead of discovering just the beginning, you also discover the end, and you say, how does the string look like in the middle? Well, it's just going to be a bridge, so you add this linear curve, and to that you add this bridge from here to there in that time interval. It's very natural. So I've just reminded all these things because I want now to move on to this mountain picture. And the mountain picture is there can we sort of repeat the same arguments that we just went through very briefly in the one-dimensional case to produce the random mountain? When I was a kid, I was fascinated by these, probably doesn't exist anymore because now we have all sorts of printers and so on. But one of my dreams was to work for the French Geographic Institute because I loved to look at maps. And in particular, I loved these little plastic type things that were, three-dimensional little maps of the Alps with in plastic. And now we want just to define what would be the natural random plastic mountain that you can define like this. So we go through exactly the same arguments, and we try to do that. So, well, we don't know how to start, so we start with the discrete version. Okay, exactly like for the random walk, for the Brownian motion. So what would be the discrete object that would be the natural random mountain? So the discrete object would be, well, we have sort of a flat piece of land, say a square. And this flat piece of land, well, at each point of this flat piece of land, you want to assign a height, right? A function z of xy. And we want to do it in a discrete way, so we just, decompose this into little squares. And on each of these little squares, like in, the booming towns around you here, we build a little skyscraper like this, Okay, so there's a height on each thing here. And we do this at random. But remember, the random walk we were defining this curve at random, but of course, at one point, you had to be at the same height than the previous one, plus or minus 1. We're just not, each point here didn't have height independent of the others. You had to hold it, together. So one way would be the following, would be to say, well, we assign an integer height at each of these things, and we impose a condition that two neighboring skyscrapers have to have a height difference of at most 1. Right? So you go back to kindergarten, you pile in your little cubes on your ground, and then you want to make something where two neighboring pile of cubes can't be of height difference more than 1. You need to do this height difference you need to allow height difference of zeros, because otherwise you might be sort of a bit constrained by this plus minus 1 story. Anyway, so here's one way to sample at random a discrete surface, which is natural. And what I'm describing to you is called the solid-on-solid model in the physics literature. It's SOS model, which would just be to say, well, on each point here, we assign an integer height, and we impose that any two neighboring guys here have a height difference of at most 1, and we choose among all these, little towns that we built like this, one uniformly at random among all possible ones. So it's just the natural analogy of random walk. That would be one way to do it. So, but there are others, of course. You could say, impose different conditions, and a little bit like here, you could say, well, instead of imposing a height difference of plus minus 1, you could just put little springs between the neighboring cells, and then say, look at what the physical model, what happens there if you are looking at this picture. Now, general question, is there a natural object that would be this analogous of the Brownian motion that will explain to you the fluctuations, a natural random continuous version of this model? The answer is yes. The first answer is yes, and this is very nice. And just this I already told you, so I don't need to repeat it. I just want to add one thing, which is something that I haven't told you here, which is namely you have to impose something about boundary conditions. You need to say something. So one natural boundary conditions, which would be the natural way to generalize the Brownian motion here, would be to say, I want the height at this corner of my carpet to be 0. Okay, and then it fluctuates. But you could do something. So this would be the analogous. You know, you hold this little carpet somehow from at one corner, and then it fluctuates. That would be the analogous thing of the Brownian motion, where you hold it at one end, and the string is open on the other end. But you can do different things. You can sort of hold it, you know, nail it down here and here. Or maybe the natural analog of the Brownian bridge would be to nail it down completely all over the, you know, impose at the boundary 0 all the way on the boundary. So that would not be a carpet. Well, some carpet would be some tambourine or trampoline type thing. You know, it's tight. It's nailed down on the boundary of your domain. So you have this notion of boundary conditions that comes into the game. Now, embarrassingly, the theory is not super, you know, strong. We are not very good at proving things about these models. But in many cases, in many natural cases, we can prove things about these limits of discrete models. What is fairly simple is to prove that the limit of these discrete models is flat, asymptotically. So typically, these mountains are flat. You need to, you know, again, in some sense, it's natural. You know, it's much, much more flat than the one-dimensional case. You know, the one-dimensional guy can fluctuate like this. It's not very constrained. But, you know, if you have a tent that is sort of, you know, nailed down on the boundary, it's harder for it to fluctuate. And the random walk is going to fluctuate in square root of n, the number of steps. And this guy, this sort of carpet, is going to move like square root of log of the number of steps. So it's going to fluctuate, you know, it's going to be very, very flat. So in particular, if you talk to physicists, and you say, we look at the random fluctuations away from the deterministic flat carpet, they will tell you, you're telling us nonsense, right? Because I know models, I know solid-on-solid model, and I know that it's flat. But it's really flat. It's just, and you say, well, it's because square root of log n is very, very small, right? Right? If you want, you need to, our object that we want is sort of the scaling, we're going to be, you know, you have to stretch in the vertical direction very, very much, and we're looking at fluctuation where n is really, really getting huge. So one has to be a bit careful about these things. However, this guy is flat, n goes to infinity. If you stretch in the vertical direction enough, you see something, and you see something that's getting closer and closer to something that is called the Gaussian free field. So the belief is that all these models I've described to you here have this property that, you know, natural models of where you have springs attached to each other, random trampolines. You look at, you know, fluctuation away from the deterministic flat pattern, you stretch in renormalize in the vertical direction until you see something, then what you see is the Gaussian free field. Embarrassingly, we don't know how to prove this for the solid-on-solid model, which is the simplest one, I think, to my knowledge, but there are a number of other models, you know, natural random surfaces where you can prove this. And a number of people have contributed to that. I'm probably going to list them in a moment. So let's go through these properties that we listed for the Brownian motion to see if they still hold. So it's the Gaussian free field. It's Gaussian. It's nice. It's a wonderful object. It's Gauss. He's there. So it combines. For me, it's sort of wonderful because it's Gaussian, and the covariance function is basically Riemann, right? So it's the Green's function. So it's a Gaussian process where the covariance function is given by the Green's function. So, you know, it has to be a wonderful object central to plenty of mathematical things. Now, again, there is a natural discrete approximation. I'll just mention it very briefly a bit later. So a little bit like there's a projection of the Brownian motion there's a natural discrete random walk. There is also, which is we like to call the discrete Gaussian free field. It satisfies the Markov property. I'm going to come back. I'm going to go through these arguments in a moment. So it has, again, exactly the same property of a similar Markov property. It's universal for very surface fluctuations, and here I listed some contributors. Maybe Giambattista Giacomini is missing here in this list. But you have papers of number of important papers that prove that if you take this discrete model of surfaces of carpets, fluctuating carpets, in the limit, you get this Gaussian free field out of the picture. And there's a new feature that wasn't present, or in some sense that was already present in the one-dimensional case, which is that this scale invariance of the Brownian bridge for this Gaussian free field becomes something much richer, which is the conformal invariance of this object. So let me just, on the blackboard, go briefly through these some of these statements. And maybe I want to first tell you about the Markov property. So the Markov property goes as follows. Imagine that you have, let's take a round tambourine, and we look at the fluctuations away from the blackboard of this thing here. And imagine we discover this mountain here. We already know, exactly what this mountain looks like here. Question, what does it look like here? What is the distribution of what remains to be discovered? You think a little bit and you say, well, the only relevant thing you need to know in order to know what happens here is to know the height of the mountain on this circle, right? Because now what I'm studying is a random tambourine that is going to be attached to this particular height on the circle here. Now, I remember that here I had this thing that the Brownian motion here that was not flat was just a flat guy to which you were adding this deterministic curve here. So what you're doing here is you're discovering here the height h on this circle. And in order to find the law of what remains to be discovered here, you are going to add a Gaussian free field with 0 boundary conditions here. And to that guy, you are going to add the natural function that is deterministic, that plays the role of the straight line before, that is going to interpolate and to find the right boundary conditions. What is the natural function that has given boundary conditions in this disk? Well, it's a solution, it's a harmonic function with boundary conditions little h. So you take the Gaussian free field, you add h, which is the solution to the Dirichlet problem in this smaller disk, right? So it's sort of the natural interpolation that you have here, and you add this fluctuation in the middle, and that's what remains to be discovered. And this is true if you start discovering this annulus or some smaller different shapes. This is going to be true. This is the Markov property of the Gaussian free field. Now, everything I'm telling you here about the Gaussian free field is known for a long, long time. So you have papers by Ed Nelson in the late 60s, early 70s called the Markov field. Okay, so understanding field theory, everything about the Gaussian free field is extremely basic. An extremely basic building block of everything that people, or many things that people did in quantum field theory a bit later. Now, conformal invariance. So what does conformal invariance mean? It means the following. It means that if I take a round tambourine, it has a certain fluctuation law, and I take a square one, is there a way to relate the law of the fluctuation in the disk and the law of the fluctuations of the carpet that is nailed down on the boundary of a square? And that's a way to look at, Riemann's mapping theorem in some sense. It should not surprise you, and in some sense, it's also another way to interpret Riemann's mapping theorem itself. But the idea is the following, is to say, well, you look at the fluctuations away from, you have this random mountain here in the disk. By Riemann's mapping theorem, we know that you can distort the disk in the direction of the blackboard in order to be angle preserving everywhere, and you can transform the disk into a square. Right? So what you're going to do is you have this random mountain here, you sample it, and then you stretch in the direction of the blackboard, you pick your random mountain by Riemann's mapping theorem in such a way that it now is not a surface, random fluctuations of a surface away from the disk, but of a square. Is that clear? That way you create a random mountain here. Conformal invariance is the random mountain you create in the square is distributed exactly like the random mountain, that the Gaussian free field in the square. In some sense, if you know how to sample the random mountain in the disk, you will be able to sample it in any simply connected domain. You just have to adjust these horizontally stretch in that direction, keeping the vertical height fixed. So in particular, this tells you that if I'm discovering, it tells you something like I have this random mountain here. You start discovering something. What remains to be discovered, right, is a random mountain in this remaining to be discovered simply connected domain. So it's still flat guy plus this deterministic harmonic function that you have to add to it. So what remains to be discovered somehow is always the same. Now, I just want to mention one thing, which is that here, these two things had, our extension in two-dimension, but much richer than the one-dimensional setting. First thing, the linear curve, well, linear functions are harmonic functions in one dimension. Okay, so it's exactly the same, the Brownian bridge. You have to add the straight line, which is the harmonic function with given boundary conditions in one dimension, to the flat guy. So this is this picture here. And the scale invariance of this one-dimensional picture now becomes, well, the conformal invariance of this two-dimensional object. So it's a very nice guy, the Gaussian free field, and it's a very elementary building block in physical field theory. In physical textbooks of field theory, it's just like, chapter 0, not even chapter 0, chapter -1. This is a trivial model. There's nothing to say about it. It's just, it's the massless free field, just natural fluctuation of something where nobody interacts with no one somehow, and that's it. Now, here comes the nice thing, and in some sense, the problematic problem is, the problematic thing is that I told you the first answer was yes, everything, life is nice, you have this object, the Gaussian free field, and then you say, well, for those of you who are probabilists and who are trained in probability theory courses and curriculum, they say, I've never heard, why didn't, I know about Brownian motion, I know about stochastic differential equation, but this story is not told so much, the Gaussian free field. Why is that? Well, it's because it's bad news, or maybe even better news, that there's one thing that is, I cheated. Everything I said is true, but I just omitted one thing, and I did something which was I give you a wrong impression. The wrong impression is that this gamma, this random mountain, is actually not a mountain. It's not a function. So what is it? It's an object. It's not a random mountain. It's not, but everything I said is true. So what is it? It's not a random function. The value gamma of x at a point, the height at a point, is not well defined. Doesn't make any sense. You can't talk about the height of the mountain at one given point. The reason is that if you draw a picture, like Kang did in Seoul here, this object that you get is like spikes that grows in both directions. And it's like a porcupine, and it doesn't have a height. It fluctuates too wildly. In some sense, it should not surprise you because it was much flatter than the random walk. So you had to stretch in the vertical direction much more until you see something, and you stretch so much that you blow everything up, and you have things at plus infinity, things at minus infinity. However, there's something you can do. And if you look at the definition is that formally the expected value of the height at the point x and the height at the point y in your random tambourine, the definition is that this is the Green's function with Dirichlet boundary conditions in the domain in which your tambourine lives of xy. So in particular, what you see that the Green's function has the bad or good property, of course, that it explodes when y goes to x. So g of x is infinite. It explodes very slowly, like log of 1 over the distance between the two, but it explodes. So expected value of gamma of x squared is infinite. So it's a Gaussian random variable with infinite variance. It doesn't make sense. However, if formally here in that formula you say, well, let's define gamma of A if I take a little piece of land here, And I want to define gamma of A, which is the sort of mean value, mean height on that land. Gamma of A would be, roughly speaking, something like the height, or the integral of the height in A. So modulo the surface, I mean, if you would divide by the area of A, this would be the mean height. Now, if you define this guy, formally what you get is that the expected value of gamma of A squared, this will be now, you just do a little bit of Fubini, and you get, this is the integral over A times A of GD of xy dx dy. And now this converges, because this explodes very, very slowly when on the diagonal, when x goes to y, is very close to y. And therefore, this guy has a finite variance. So what you're going to do is, instead of defining gamma as a function that assigns to each point a height, it's going to be a function that assigns to each piece of land, A, the mean height on A. So, you can say it's a random radon measure, or random distribution, or however you want to call it, but it just says what you can't make sense of the height at one point, but you can make sense of the mean height of this generalized random mountain on each the open set A. And in fact, this mean height, you can also make sense of the mean value of gamma on a circle, on the line, because log of 1 over x minus y, if you integrate it on the line, this still is sort of nicely converging. So it's Gaussian. Everything is true. Conformal invariance is still true, because you just look at the area, you just stretch whatever you define here, you stretch it in the other direction, and you get the natural way to define it there. And the Markov property still holds. And that's the interesting thing. I discover this, whatever it is, here. How do I define what remains to be discovered? It's this Gaussian free field and the remaining to be discovered thing, to which I add this harmonic interpolation of the boundary condition. What is a harmonic interpolation? What is the value of the harmonic function, say, in the middle of this disk? It's just the mean value on the circle, right, of little h. And the mean value of gamma on the circle makes sense. I just told you, you can make sense of what the mean value of this wild thing is on one-dimensional curves. So the harmonic function here, h, which is the harmonic extension of the Gaussian free field that you view on the circle, makes sense. It's the harmonic function, which has boundary values that sort of start fluctuating like crazy on the boundary, but still has a nice harmonic extension inside. So it's nice because, in some sense, here you have an instance of, we said, let's take a function at random, Brownian motion. Oh, it's a function. It's a wild function, but it's a function. So here, let's take a surface at random. Well, it's not a surface. It's something that got exploded, but it's still something you can define, and it has features like this. However, once you were there, then the physicist said, yeah, mathematicians go out of the way. You have nothing to tell us about this object. There's no, it's there. It's defined formally now. It's formally. You have a covariance function structures, and what you do is you can define things like that play the role of what physicists like to call correlation functions, and define this type of things. But there's no surface anymore. It's not a surface. And now what I want to explain to you very briefly in the remaining 15 minutes is that, well, still, actually, it's not true. There's a lot to be said about the geometry of this guy, which is this wild object. And you can draw something which looks like drawing a topographic map of this Gaussian free field. And maybe, so you want to say, can you still, describe it really like something that gives you the feeling that it's a surface? And if you can do that, maybe you have access to something really interesting there, because it's a natural object that is good. Has to be related to all sorts of nice mathematics. So what I want to explain to you now is sort of what is going on these days, a little bit on this direction. And a number of people involved there, so it's not, I'm one of the number of people who have, looking at this. So one important name in this entire picture is Scott Sheffield, who's one of the driving forces in this. He started this with Odette Schramm some 10 years ago or something like that, maybe, or 8 years ago. And there's really a lot of contributors, and I'll try to mention, not to forget to mention them. But still, what I'm telling you now is the following story. Imagine that you want to discover a surface. And you see, you have this sort of Markov property of the Gaussian free field. And the Markov property of the Gaussian free field now is a Markov property in space. Right? So the time now is not, this one-dimensional line, is the two-dimensional, it's the two-dimensional space. So if you, know about Brownian motion and so on, there's this notion of stopping time. You can start sort of exploring and stop depending on what you have explored so far. You can devise exploration strategies. So a natural exploration strategy, if you have to discover a mountain, is the following. Imagine you have a mountain which has boundary value 0 here. A real mountain, a smooth mountain. And you have an army of people at your disposal here on the boundary of the mountain, and you tell them, you want to give them tell them go and explore everything you can, but the rule is you're not allowed to go above level +10 or below level -10. And try to go wherever you can without that. So what these guys are going to do is they're going to invade everything here until they meet these first level lines at height plus or -10. And then they are blocked. They can't go above +10 or below -10. So they invade everything here, which is between the part which is between level +10 and -10 that you can access from the outside. Now, when they get here, they have some sort of plateau thing. And now here you have a surface that is going to be attached with flat boundary values, +10 or -10, depending on whether the level line you observe is what it has. And this Gaussian free field has this feeling that it can be explored in a Markovian way. So imagine that you could explore the Gaussian free field in this way. You tell to your army of people, go and explore everything without going above +10 or -10. Well, you would imagine that the law of what remains to be discovered here, because these are the natural fluctuation uniformly, etc. If you look at the discrete models, this is the natural thing. Here, if I discover a level line as +10, then the natural fluctuation, what is the law of what remains to be discovered here? It's a Gaussian free field with boundary conditions +10. And here it's going to be another Gaussian free field with boundary conditions, say, -10, if this is a level line of -10. And this fluctuation here is going to be independent of that one here. Plus, you have conformal invariance, so you know that even though the boundary might be a bit wild here, you know how to do that because it's just always the same business you have to iterate. So on the other hand, you say, well, this doesn't make any sense because it's not a surface. So how, my army can't just, move around and do this. Well, it turns out that you can do something of that sort. And this is the picture I showed you at the beginning here. There is a random way. There is a way that I'm not going to tell you how we do that, right? But there exists a way to choose at random a picture like this. And this picture, well, you might not view it as a very nice topographic map, but you should think this picture as a set of loops. Right? You have the disk here. And you have these loops. The inside of the loops is white. Each loop has a boundary. Each white piece has a boundary, which you look at as a loop. Now, this object that you see here, that has been simulated by David Wilson, he's our simulation hero in our area. He knows how to simulate everything very quickly and very nicely. And this object here we have this in our bag of tools, and there's something that tells us that this is we strongly believe that this looks like the first, mountain the first level line, collection of first level lines. So you have really a collection of these things. So if you believe in this, this random picture has a number of properties. The first one is that there is conformal invariance. So in particular, this picture is hyperbolic in the sense that if you perform any Möbius transformation of the disk to that picture, clearly you see a different picture, but the law of the picture you observe is the same. And if maybe for those of you who are hyperbolic people, they looked at this picture and said, Escher or whatever, when I get closer to the boundary, it looks like this hole, near the boundary looks a bit like the hole in the inside, or, It's not self-similar, but it's self-similar, it's invariant in the Möbius transformation in law. So we have this way to construct these loops. Now, what we're going to do now is the following. It's better to do it like this. We first sample the previous picture, and we draw the loops like this. Now, this loop, this collection of loops, you should really think of it like a carpet. Right? If you remember the Sierpinski carpet, like this picture, the Lebesgue measure of the white part is 0. Right? A typical point, the typical point will be in a black square. So it's the same thing here. So the Lebesgue measure, or the mass of the black set here, is 0. It's a sponge which has 0 area. Now, when I look at the Sierpinski carpet here, you should think really of this previous picture as the continuous analog of the Sierpinski some analog of the Sierpinski carpet. Now, what you do is the following. You sample this picture, the previous one. Now, in each of the loops that you find, you toss a coin. So that's the procedure, I think, basically, first appearance in the paper of Miller and Sheffield. You toss a coin for each of these loops, if independently of each other. If it's heads, that means it's a level line plus 10. If it's tail, it's a level line minus 10. So they have different colors. And now, in each of the loops, you iterate again. You do the same picture again in law. Right? So you resample the same random picture independently inside each of these loops. And now you resample in each of the loops you find, you orient them, you say you go up or down independently. So now after 2 steps, what you have defined after 2 steps is a function that you can call h2 of x that takes values -2, 0, or 2, depending if you went twice up or twice down or once up and once down. And it's defined on a set of full Lebesgue measure, because the guys that were outside of the first loops had 0 Lebesgue measures, and then inside of each of the loops you were starting again, so a given point, x, has probability 1 to be inside the loop at first level, and therefore it has probability 1 to be inside the loop at the second level, and so on and so on. Now you define a random function h2, a random function h3, and so on. Right? So you do go down in scale like this. And therefore, you define a sequence of functions hn of x, which is a sequence of functions that you define. Of course, in my tool bag, I have used what we call the conformal loop ensemble with parameter 4, which is this random way to generate the first picture I showed you. But if you have this random way at your disposal, you do it once, and each side of each loop that you find, you sample this again, and you get the random function hn. Hn is a random integer-valued function. Now, what happens to the sequence hn of x if I fix x and I let n go to infinity? What happens to this sequence? Well, it's just a simple random walk, because at each step I will be surrounded by a loop, and I go up or down depending on what happens to my nth generation loop around it. So hn of x, when x goes to infinity, doesn't converge to anything. It's a simple random walk. It oscillates wildly. What happens to the covariance between the, can you say about how the height of this guy and the height of this guy, hn of x and hn of y, are related to each other? So they're going to fluctuate again together as long as the loops that surround them both. And at some point, like here, this one is inside this loop, this was inside this other loop, and then this will fluctuate like a random walk independently of this one. So what is the expected value of hn of x times hn of y? It's the expected number of loops that surround them both. So in particular, when n goes to infinity, the expected number of loops that surround them both will be finite, because at some point they will, separate. So hn of x, this reminds us something. Hn of x doesn't converge when n goes to infinity, but the expected value between hn of x and hn of y converges when n goes to infinity. So the theorem is the following. If you define for any a, you define hn of a, which would be just the mean height over a of hn of x. I mean, not the mean height, but the, this thing. And you say, well, there's a problem because hn is not defined everywhere, but you don't care about what happens outside of the loops. It has 0 Lebesgue measure. It doesn't count here. So you define this, no problem to define this. Now, hn, in this sequence of thing like this family indexed by the open set A here, this process, when n goes to infinity, it converges to the Gaussian free field. And this is an almost sure statement. It's not a statement about, in distribution. Just say this, the height hn of A converges almost surely when n goes to infinity to something. And this something is exactly a Gaussian free field. How could that be? Well, what happens is that all these guys are going to fluctuate, going up and down, but there's some averaging up phenomenon because these cells are fluctuating, but they are smaller and smaller cells, and the vertical fluctuation is much smaller than the actual area of the corresponding thing. So what happens is there's an averaging out phenomenon, law of large number type things, that says that these very small fluctuations are averaged out, and the hn of A converges to something. So in other words, what I've described you via using just this first picture here, you start with that, and what you have discovered is exactly a topographic map of the Gaussian free field, because here in the end you would construct exactly the entire information about the Gaussian free field. So the Gaussian free field has a topographic map. It's not a surface, but there are lines lying there. And you can it has a topographic map, and you can do all sorts of geometric things with the Gaussian free field. Now, don't worry, I know that I'm almost out of time, but it's fine. I just want to make a couple of comments about that. The first one is that it is a surface. It's not a surface, so there's something different than in the normal surface. Namely that I have chosen my topographic map with level lines plus 10, minus 10. I cheated. There's just one precise height of level lines. Plus 10 is if you normalize the Gaussian free field well. Otherwise, you have to take the level lines at height square root of pi over 8 or something like that. So there's a given height, right, for which this will work. But then usually when you are looking at a topographic map with level lines plus 10, minus 10, you don't have the information about the entire surface. It's just an approximation. What happens in between these level lines, you don't have access to. Here you have access to everything by just looking at these level lines, but just basically because there's no space in between them in terms of area. So it's not a surface, but it's something that you can describe by level lines in a much better way than our usual surfaces in some sense. Now, what I want you to just conclude with is just a list of ongoing work on this story. And here, there's an important theorem. Here I constructed the fact that Hn converges, gives a construction of the Gaussian free field. Now there's a converse theorem, which is very difficult, I think, well, not easy to read at least, which is due to Schramm and Sheffield and to vedada, which is say that if I take the Gaussian free field, there's just one topographic map corresponding to it. So deterministic, the topographic map is a deterministic function of the mountain, if you want. Now, here just a few list of ongoing research. The first thing is there's sort of, this is related to quantum gravity, like what we like to call, because in some sense you see that this random mountain can be used in order to try to define random metric structures on the disk. If you take the exponential of the Gaussian free field, this will tend to be something positive, and you can then try to use this in order to define distances. It's very vague. There's an important discrete work that has been going on in the last couple of years, which has to do with take discrete two-dimensional planar graphs, which we like to call planar maps. Let's choose a graph like this at random and take the graph distance on it. Take a very large sample of that. Then this will converge in the sort of Gromov-Hausdorff metric, Gromov-Hausdorff sense, to a random metric space in the scaling limit. And this random metric space should be very closely related to the previous one I mentioned by taking the exponential of the Gaussian free field. Big open question. Now, you can do this, you can view this also in terms of random weldings. For those of you who are coming from the conformal world, you know that an interface like this is a natural way of welding together two conformal structures. So you have a random conformal structures. Clearly, behind the scene, there's the fact that you have this Schramm-Leuven evolution, which are there, because these boundaries here of these level lines, I didn't tell you, they are fractal. Not a surprise, because the surface is fractal. They are one of these Schramm-Leuven evolution. The level lines have fractal dimension 3/2. That's just how life is. Now, you can define all sorts of generalized topographic lines, or things that they like to call light cones and all sorts of things in there. Instead of walking being flat, you put someone on this mountain with a pair of skis, and one foot is a bit shorter than the other, so he goes down the slope but always turning in a certain way, and this will define a sort of a random function, all the other SLEs. Now you can do analysis, and this is what I find very interesting now is in the carpet. Now you just look at what happens in this fractal set. In this carpet, you can start to do complex analysis. So you can try to define the natural notion, because there's conformal invariance and there's a lot of structure in there. You can define Laplacian. You can define you can look whether Kuiper's uniformization theorem works still for these fractal objects. So you can prove, and that's ongoing work by Rode and Werner, that sort of says, yes, there's this first carpet, this random fractal picture I showed you, has a uniformization into a circle domain, a circle Sierpinski something. And you can do, what we're doing now with Jason Miller, is inside this carpet, you can do something that plays the role of critical percolation. And you can view that inside this carpet, you can sort of start defining all sorts of structures that have conformal invariance built in when you look at the two-dimensional object. But here, using this conformal structure and the fact that you have conformal invariance in law of these guys, the conformal tools are still, can be adapted, and you can do, in some sense, what happens is that you can do there's a conformal structure sitting in this Sierpinski structure. So you have domains random domains with dimension between 1 and 2, which is these like generalized natural Sierpinski, Cantor, two-dimensional Cantor type sets. And these objects have inside them a lot of complex analysis. And they have some intrinsic, complex structure. You can view this as some notion of, there's a natural Riemann surface type structure sitting there in this carpet, even though it's an object which has 0 Lebesgue measure and is very fractal. And of course, this is all due to the fact that we started with, Riemann, Gauss, and you take these tools, you play around, and what you get is fun. So, thank you for your attention.
As expected, this was a very impressive and very beautiful lecture and presentation of deep results. We don't know where you're going to, but let's ask the audience for questions, comments? Please, I open the floor. Okay, Maria Elena.
It's simple to say the interpretation of this step, which works.
Can you repeat? We are making good sounds of the lectures and pictures and so on. So please.
The interpretation of the step, which
Yes.
works.
Well, in some sense, it gives me the opportunity. This question is a good question because it also gives me the opportunity to say something more about what I haven't said. These lines are not exactly level lines because if you think about it, inside, so, it's nailed at 0. If you take the guy with boundary value 0, it's nailed at 0 on the boundary, but it doesn't mean anything because it doesn't have a height. But what happens is that if you get closer to the boundary, you have these little things that are here. So if you take the mean value of your object near the boundary, you get something that is very close to 0. So in particular, what happens is that if you take the mean value of what you get here from the inside, it's very close to plus 10, right? If this is a level line of left. And if you take the mean value of what you see outside, what is it? Is it plus 10? That would be a level line. Well, no, because here outside, well, there's no area, right? But you have plenty of other small loops here. One out of two of them has height plus 10. One out of two has height minus 10 because you tossed a coin. And so the mean height when you approach from the other side is 0. So in particular, what you get is that these are not level lines, they are cliffs. It's like a cliff where on the one side you are plus 10, on the other you are 0. So it's a little bit, the picture is like, if you think about the initial picture, it's like you have little podiums, not all about, like here. And somehow what happens is that on one side, basically you have a natural sort of notion of cliffs that are all around the place here, in this mountain. So this plus 10 or square root of pi over 8, or depending on how you normalize these things, and I never know how to do this because I have I think half of the mathematicians, the problem that I never know how to normalize the Green's function. I never know if it has 1 over pi, 2 over pi, or let's just forget about it. And anyway, so there's this square root of, you know that GD has a... Anyway, so it's a cliff, and there's a natural notion of cliff in this random mountain, and of height, natural height of cliffs that would create these lines. So this would be one way to interpret this notion of height. Now, just to stimulate your imagination, you might say, well, but are there cliffs between plus 5 and plus 15? If there were cliffs between... And the answer is, yeah, of course, because if you look in the inside, somewhere here in the inside, the Gaussian free field with height boundary value 0 has is absolutely continuous in distribution with respect to the Gaussian free field boundary values plus 5. And so you have this topographic map, which corresponds to 0, 10, 20, these cliffs. But you also, in the same picture, you have another topographic map with plus 5, minus 5, plus 15. And these cliffs will bounce on each other all the time, because the cliff between plus 5 and plus 15 will be higher than the cliff between 0 and 10. They can't cross. So you have all these things, and so these are the type of structures that Miller and Sheffield are exploring.
More questions? I'm avoiding you for a moment.
Hi, I was just wondering how you use this thing to define distance. So does the Gaussian free field give you like Lipschitz functions on almost every line or something like that?
Okay, so the first thing is that we don't know how to define a distance. We know to define something, which is we know how to define lengths or things like that, but we're not quite sure how to extract, where the geodesic is, and so what the distance. So there's a big question mark. But what Sheffield and Duplantier did was you can define something, and this something was basically it's adaptation of Kahan's stochastic cascades that they were starting with in the context of the Sierpinski version. And the idea is basically to say each time you cross a line, when you go up a cliff, that's basically the idea. If you go up the cliff, you are twice larger, and if you go down the cliff, you are twice smaller. Right? And then you want to say, well, okay, or let's put it this way: if you go cliff up, you have to pay petrol is twice more expensive, and if you go down, it's twice cheaper. And then you say, where's the how do I go from here to here with the? And you say, well, this doesn't work. So what you have to do is, instead of saying, because it's multiplication, the mean value between 2 and 1/2 is not 1. So what you have to do is, basically, I'm just simplifying, but what you have to do is say, well, if I go up a cliff, I have to pay 20% more, and if I go down the cliff, I pay 10% less. And then if you adjust this well, then you have some nice notion of defining sort of how much it costs you when you travel along certain paths, something like that. For those who are coming from quantum field theory, basically, you might have heard that when something is not well defined in the Gaussian world, like something exponential of gamma, there's a trick. You put dots here. This is what I just tried to describe. So, Vic product, chaos decomposition, you subtract sort of the mean value, which is infinite in this guy, and then you get something nice. So this.
Questions, comments? I didn't forget you. It's impossible. Questions, comments? Okay, very, very specific, to the point, please.
Thanks. You connected it to the lecture to physics, but in physics we have imprecision, we have uncertainty. So my question is about stability. If there are some known results about if some parameters are changed a little bit, then the picture or something like this will change a little bit.
It's a very good question. So there's a lot of results about stability of this type of systems. Not exactly this one, but and these are results that the physicists don't like in some sense, because it's more coming from computer science type structures, So if you are looking at, say, these models have the property that, they have a natural dynamics underneath them in some sense. Everything is Gaussian, can be viewed at the mean value or something. There's a stationary version of what's called Orsay and Uhlenbeck of a fluctuating carpet now, And the idea is that basically if you do a little mistake somewhere, if by reading your structure slightly differently, well, the Gaussian free field might be fairly stable, but the lines that are sitting in there they're very unstable. So in some sense, a tiny difference in the Gaussian free field might create a completely different topographic map. So this is exactly the realm of. In some sense, you can view it like this. You can view these pictures, and in some sense, you sense it as a fixed point of renormalization map that goes, because here you have this guy, and then you sample it at random, and then you get the guy at the next level, in some sense. And this map is extremely unstable. I don't know if this makes a lot of sense. So what I'm saying is the following. Imagine that you know the Gaussian free field at 99% of the space. And you resample it just at tiny places. What happens, the topographic map that you get is just completely, well, not completely changed, but it changes much more than the standard structures that you would get when you take sum of random variables, despite the fact that it's Gaussian and it's nice. So this two-dimensional world is extremely noise sensitive, and there are a number of results. So if you look at papers by Steiff, Garban, Schramm, Benjamini, Kalai, noise sensitivity, you will see that this is not for these models. Usually it's more for percolation, which is a simpler model that you can understand. But it's actually one of those models where you get something really fun. So for instance, one theorem by Schramm and Smirnov is saying that in an analogous, slightly analogous picture of percolation, the noise that is sitting in the two-dimensional, that in the two-dimensional space is not white noise; it's a black noise, like Cyrilson likes to call them. So it's a type of noise we have very hard time to actually understand or on intuitive level. So you have this microscopic structure, in some sense. If you come back from another way to view it is the following: you have some guys sitting. You have this random carpet. You have in the discrete world. You have one person sitting on each skyscraper, which is looking, doing something at random to adjust, and then you have the global structure at the end. What happens is that most people sitting there will have no influence on the macroscopic pictures, but a tiny proportion of these guys sitting on this boundary of the skyscrapers, in the end, will have had a tremendous influence, because if they would have done something different, then the entire topographic picture would have changed. So this type of these are not theorems by any way, right? So this is probably true, and probably people are going to work on it.
Okay, more questions, comments?
Here's one.
Oh, yeah.
Okay, I was just wondering, another question. If you take the Gaussian free... Actually, I've got lots of questions I'd love to ask. If you take the Gaussian free field in a square and then take a wavelet transform, does that give you something nice? Wavelet transform. So something nice is something different from a Fourier transform. Does that give you a whole series of independent random variables?
No, I don't think wavelets... I mean, if you do a Fourier transform, then it's independent Gaussian input.
Okay.
So you can view this, the Gaussian free field, I didn't say it, but that's one way to look at it. It's just you decompose the Dirichlet Laplacian in your domain, and into eigenvalues. So clearly this is nicely related to conformal invariance, and they are all related to each other and so on. And then you say, well, this is going to, let's take independent Gaussian entries. And if you remember, if you look at this picture here, you get, it's sort of obvious. So it's a natural random Fourier series, two-dimensional random Fourier series attached to a certain natural L2 Hilbert space. Well, not L2, but the natural Hilbert space associated that you want to put in this. So it's a random Fourier series, but it's diverging pointwise. But if you integrate it out, it's converging. That's one way to see it.
Okay, so through mountains, you have reached, and your colleagues, 3 dimensions.
Yeah. Well,
perhaps more.
Yeah, I mean, it's this, everything here is very two-dimensional, right? I mean, it's everything works because there's complex analysis, and we are subsets of 2 dimensions. But clearly, it's very tempting to try to define something, and the physicists tell us, look in that direction, some sort of, maybe there's this, a third-dimensional dynamics in a different dimension, and where then you start, 4-dimensional. Okay, I don't know. But it's tempting to try to view this as sort of some crosscut or something. But
I am sure that when you come back here in a few years,
I'm sure I won't tell you something. I will come back, but I'm sure I won't be tell you. I will not tell you about string
theory. Thank you
theory.
very much for this beautiful lecture. That's applaud. Then then we're going to celebrate this beautiful lecture with a cocktail outside.